There is a clock on your wrist right now, or on your phone, or somewhere in the room, and it is telling you the truth. 1 second, then the next second, then the next. All the same size, all in a row, marching forward the way they always have. You have trusted that clock your whole life. It has never once lied to you. Tonight we're going to break it. Not with a trick, not with a story, with something real, something the universe actually does to time when you get close enough to the right object. Because there is a place out there, a real place, where your clock and the universe's clock stop agreeing. Where 1 second on your wrist is not 1 second out in the stars. Where the gap between the two grows so wide that you might fall for what feels like minutes, while behind you galaxies are born and die and forget they ever existed. That place is the edge of a black hole, and tonight you're going to fall into one in real time. Here is what I mean by real time, because it matters, and it is the strangest promise I have ever made on this channel. This video is about 2 hours long. The fall we're about to take is going to last, from your point of view, from the point of view of the person actually falling, roughly that same 2 hours. We're going to move together, you and I, down through the layers of one of these objects at something close to the pace you would actually experience it. When the video says you have an hour left before the end, you will have, more or less, an hour left. When it says minutes, minutes. The runtime of the thing you're listening to is the countdown of your own fall. So get comfortable. Lie back. You do not need to hold on to anything, and I will explain why shortly, because the not holding on is one of the gentlest and most surprising parts of all of this. For now, just settle in. Your fall has already begun. It began the moment you press play. Now, before we go any further, I want to take the most common picture of a black hole, the one almost everyone carries around, and set it gently aside, because it is going to get in our way. When most people imagine falling into a black hole, they imagine two things. They imagine a violent death, crushed and torn and screaming, over in an instant. Or they imagine the opposite, a kind of magic portal, a doorway to another universe, a tunnel you slip through into somewhere else. Those are the two doors people argue about, the shredder or the portal, the end or the escape. Here's the thing, neither of those is quite what the physics says. There is a third door, and it is stranger and quieter than either of the other two, and it is the one we are walking through tonight. Because the truth about falling into a black hole is not mainly a story about death, though death is in it. And it is not a story about escape, because there is no escape. It is a story about time, about what happens to your sense of 1 second after another when the thing pulling on you is heavy enough to bend the clock itself. The black hole does not mainly crush you, it does not mainly transport you. What it mainly does, the thing it does that nothing else in the universe can, is it takes time, your time, ordinary, reliable, forward-marching time, and it pulls it like taffy until it no longer looks like time at all. That is the fall we're taking. It is, at the very least, a real possibility allowed by the physics, not a fantasy. Not a fall through space, really. A fall through time, with space coming along for the ride. By the end of tonight, you're going to understand something that took physicists most of a century to make peace with, and many of them never fully did. You're going to understand why the most frightening thing about a black hole might not be what happens to you inside it. It might well be what you see when you turn around and look back out. But I am getting ahead of us, and we have 2 hours. There is no rush. That is maybe the one luxury this particular journey gives us, the luxury of falling slowly. So let us start where any honest fall has to start, not at the edge, far away, out where the black hole is still just a dark idea against the stars, and you are still safe, and your clock is still telling the truth. Let me tell you what we are actually falling toward, because the word black hole does a lot of hiding. Picture for a moment, not a hole at all. Picture a ball, a perfectly dark sphere hanging in space, and around it a faint warped shimmer where the starlight behind it gets bent and smeared, like looking through the bottom of a glass. The sphere is not made of anything you could touch. It is not a surface. It is a boundary, a line drawn in empty space, and the line marks one simple, absolute rule. Cross this, and you cannot come back. Not because something stops you, because every direction that used to lead out now leads in. That boundary has a name, the event horizon, and almost everything tonight turns on it, so hold on to the name even though I told you there was nothing to hold on to. The event horizon is not the black hole exactly. It is the point of no return around the black hole. The real heart of the thing, the place all the masses collapse down to, sits far below, and we will get there, near the end, in the last minutes of our fall. But the horizon is the door. And the most important fact about this door, the fact that makes our whole journey possible, is this. For a big enough black hole, you can cross the door and feel absolutely nothing. No wall, no jolt, no barrier. You drift across the most absolute boundary in the universe the way you might drift across the state line on a dark highway, asleep in the back seat, never knowing the moment you passed it. Which black hole are we falling into? That choice matters more than you would think, so let me make it carefully, because the small ones and the big ones offer you completely different deaths. The small black holes, the ones that form when a single large star dies and collapses, are only a few times heavier than our Sun, but they pack all of that into a region just a few miles across. Those are vicious. Their gravity changes so steeply from your head to your feet that you would be pulled apart, stretched into a thin stream, long before you ever reach the horizon. Physicists have a word for this, and it is the only genuinely silly word in all of serious physics. Spaghettification. You would be turned into spaghetti. For a small black hole, the death is real and it comes early and there is nothing slow or gentle about it. But we are not falling into a small one. Tonight we are falling into a giant, a supermassive black hole, the kind that sits at the center of almost every large galaxy, including our own. These things are millions, sometimes billions, of times the mass of the Sun. The one at the heart of the Milky Way, called Sagittarius A star, is about 4 million solar masses. And here is the beautiful, counterintuitive thing about the giants, the thing that lets us fall in one piece. The bigger the black hole, the gentler the crossing. Because the horizon of a giant is so enormous, so far from the center, that the stretching force where you cross it is mild. Mild enough that you sail through the point of no return completely intact, completely calm, your body whole, your clock still ticking in your own hand, with no sign at all that you have just done the most irreversible thing a human being can do. That is the fall worth taking. Not the quick shredding of the small ones. The long, quiet, impossible descent into a giant, where death waits, yes, but waits politely far below, and gives you the whole long fall to think about what is happening to you. So that is our destination. A supermassive black hole, dark and enormous and patient, and we are still right now a long way out from it. Falling, picking up speed, the dark sphere ahead still small enough to cover with your thumb. We have a long way to go and a strange amount of time to get there, time that is about to start behaving in ways that will test everything your wrist has ever told you. So let us fall a while and watch what happens to the clock. Before we go deeper, I want to clear away a few things that almost everyone believes about black holes, and that are not quite right, because they keep getting in the way of the real strangeness, which is better than the myths. The first one is the big one. People think black holes are cosmic vacuum cleaners, roaming the galaxy, sucking everything in. They are not. A black hole's gravity is not special in its reach. It is just gravity, the same gravity any object of that mass would have. If you replaced our Sun, right now, with a black hole of exactly the same mass, the Earth would not get sucked in. It would keep orbiting in exactly the same path as if nothing had changed, just colder and darker. The orbits would all hold. The only thing that makes a black hole dangerous is getting close, very close, far closer than the original star's surface would have been. From a safe distance, a black hole is just a heavy thing you orbit, no greedier than any other heavy thing. The galaxy is not slowly being drained. The giant at our center holds the Milky Way together, yes, but it does not eat it. the second one. People imagine the black hole as a hole, a funnel, a drain you fall down, usually drawn as that curved grid dipping into a pit. That picture is a two-dimensional cartoon of something that is fully three-dimensional. A black hole is a sphere, not a pit. You can fall into it from any direction at all, from above, below, the side, any angle, and it is the same. There is no down to it from the outside, no special funnel orientation. The dark sphere we have been falling towards swallows from all sides equally. The drain picture is just an attempt to draw curved space on a flat page, and it has misled almost everyone who ever saw it. The third. People think the horizon is a physical place, a surface, something you would smack into or feel. We have already lived the truth of this one together. The horizon is not a thing. It is a line drawn in empty space defined purely by a fact about the future, that past it, all roads lead in. You feel nothing crossing it. There is nothing there to feel. It is the most consequential nothing in the universe, and the fourth, the one I find the most quietly important. People assume that to fall into a black hole is to be destroyed quickly and violently, and that therefore the whole subject is one of horror. But for a supermassive black hole, as we're seeing tonight, the fall is long and calm. And for most of it, you are unharmed, weightless and clear-headed, with time to look around. The violence, when it finally comes only at the very end and comes fast. The dominant experience of falling into a giant is not pain. It is awe and a strange peace and a slow unfolding of the most disorienting views any eyes could ever take in. The horror story is mostly wrong. What replaces it is stranger and, in its way, gentler. The black hole does not lunge at you. It receives you slowly and gives you the whole long fall to understand what's happening before it asks anything of you at all. I clear these away not to lecture, but because every myth we drop makes the real thing easier to feel. The truth does not need the exaggerations. A sphere of dark that bends time, that you fall into peacefully from any direction, that holds your last image frozen at its edge forever, while you drop calmly through to a mystery at the center, is so much more interesting than a roaring drain that eats the galaxy. Let the cartoon go. What is actually out there is better. For the first stretch of our fall, almost nothing happens. That is worth saying plainly, because the movies never show you this part. There is no roaring, no spinning, no alarm. There is just you and the dark sphere ahead, slowly growing. You're falling faster every second, but falling in space does not feel like falling. It feels like floating. There is no wind, no ground rushing up, no sense of speed at all. If you closed your eyes, you would not know you were moving. This is the not holding on I promised to explain. When you fall in a gravitational field, you and everything around you fall together at the same rate, so you feel no force at all. Astronauts on the space station are not floating because there is no gravity up there. There is almost as much gravity at that height as there is on the ground. They are floating because they are falling constantly around the Earth, and falling feels like weightlessness. You, right now, falling toward this black hole, feel exactly that. Perfectly weightless, perfectly calm. The most dangerous journey imaginable, and your body thinks it is resting. So rest. We have time. As we fall, let me tell you what is starting to happen to the light, because the light is the first thing that changes, and it changes before anything touches you. The black hole ahead is dark, but the space around it is not always empty. Many of these giants are wrapped in a vast flat disk of gas and dust, spiraling inward, heating up as it crowds together, glowing. If our black hole has one of these, you're seeing it now, a brilliant ring of light around the dark sphere tilted across your view. And as you fall toward it, that light begins to do something strange. It begins to gather, to concentrate. The whole sky, all the stars behind you and to your sides, starts to slide forward, crowding into a brighter and brighter circle ahead of you, as if the universe was slowly being funneled toward the place you're falling. This is the bending of the light by gravity, and the deeper you fall, the more extreme it gets. The view ahead grows brighter and more compressed. The view behind grows dark. Let me slow all the way down now and just describe what you actually see, because we have talked a great deal about time and very little about the view. And the view near a black hole is unlike anything human eyes evolved to take in. I want to walk you through it slowly, the way you might let your eyes adjust to a dark room. Early in the fall, from far out, it is almost ordinary. A dark circle ahead, the stars behind it and around it. But as you fall, the black circle grows, and the first strange thing you notice is that the stars near its edge are not where they should be. The black hole's gravity bends the light passing near it, so the stars appear to slide away from the dark circle, pushed outward, and the ones that should be hidden directly behind the black hole are smeared into a thin, bright ring around its edge. That ring of bent starlight is called an Einstein ring, and it means you can see, in a sense, around the black hole. The sky directly behind it is wrapped and presented to you as a glowing halo encircling the dark. As you fall closer, the bending grows more extreme, and the whole sky begins to shift. Everything ahead of you, and even to your side, starts to crowd forward, the entire field of stars compressing toward the front of your view, as though you were diving into a tunnel, and the whole universe was sliding around to gather at its mouth. Behind you, the darkness grows, not because there is nothing there, but because the light from behind is being bent forward, away from your backward gaze. The cosmos is being funneled. The dark circle ahead is now ringed and layered with concentric arcs of distorted light. The same stars appearing more than once, bent into multiple images, the sky folding over on itself like a reflection in a curved spoon. Then you reach the photon sphere, that region where light itself can orbit, and here the view becomes genuinely impossible. Because light can circle the black hole here, you might see images that have looped all the way around. Glance to the side and you may catch the back of your own head, faintly. Light that left you, travelled around the black hole, and came back to your eye from the far side. Look toward the dark and you might see infinite nested rings, each one light that has gone around the black hole one more time than the last. A stack of ghostly repeating skies crowding into the edge of the shadow, fainter and fainter, the universe reflected in itself an endless number of times around the rim of the dark. And the colours shift too. As you fall, the light coming from ahead is blue shifted, squeezed toward the blue and violet and beyond by your plunging speed and the gravity, while any light reaching you from behind is reddened, stretched toward crimson, and then into the invisible. So the funnel of crowded light ahead is not just bright. It is shifting in colour, intensifying, the whole compressed universe glowing harder and bluer as you fall toward it, while the world behind goes red and dim and finally dark. I describe all this slowly because I think it matters to know that the fall is not, in its texture, a horror. It is a kind of overwhelming silent beauty. No eye has ever seen it, and no eye ever will and live to tell it, but the physics lets us reconstruct it, and what it reconstructs is a slow blooming of impossible light, the entire sky gathering and brightening and folding into rings ahead of you, while you drift down in perfect, weightless quiet. If you're going to fall into the most extreme object in the universe, at least the view, right up until the very end, is something close to sublime. Let that be the picture you hold. Not a roaring drain, a silent descent into a deepening, brightening, endlessly folded light. But the thing I most want you to notice on this part of the fall is not in front of you. It is behind you. Because if you could see a clock back on the world you left, a clock held by someone who stayed behind and watched you go, you would notice that their clock is running fast. Faster than yours. A little faster at first, then noticeably faster, then alarmingly faster. This is the heart of everything, so let us sit with it gently, the way you would sit with a hard idea at 3 a.m. when there is no one to rush you. Time does not run at the same speed everywhere. We tend to assume it does, because here on Earth, where we all live at roughly the same distance from roughly the same gravity, it nearly does. But time runs slower when you are deeper in a gravitational field. Closer to a heavy object, your clock ticks slower, measured against a clock that is farther away. On Earth, this effect is tiny, almost too small to notice, though it is real, and we have measured it, and the satellites that tell your phone where you are have to correct for it constantly, or they would lead you to the wrong street. Tiny here, but near a black hole, it is not tiny. Near a black hole, it is the whole story. I want to stay with that small Earth effect for a moment. The tiny one, the one I said was almost too small to notice, because there is something wonderful about it, and it makes the whole rest of tonight more believable. You carry the proof in your pocket. The navigation on your phone, the little blue dot that knows which street you're on, works by listening to a fleet of satellites orbiting about 12,000 miles up. Each satellite carries an atomic clock, and the way your phone finds you is by comparing, with breathtaking precision, the tiny differences in when each satellite's time signal arrives. We are talking about timing accurate to billionths of a second, because light and radio move so fast that even a billionth of a second of error puts you off by a foot or more. Now here is the part that matters for us. Those satellites are farther from Earth's mass than you are, standing on the ground, which means, by exactly the effect we have been talking about tonight, their clocks run a little faster than yours. Higher up, weaker gravity, faster time. The difference is small. It comes out to about 38 millionths of a second per day. That sounds like nothing. It is not nothing. If the engineers did not correct for it, that error would pile up, and within a single day your blue dot would drift off by several miles. The whole system would be useless inside of an afternoon. So every GPS satellite has the correction built in. The clocks are deliberately tuned before launch to tick at what looks like the wrong rate from the ground, precisely so that once they are up there in weaker gravity, running faster, they end up matching our clocks down here. Engineers correct for the bending of time as a matter of routine every day, or your phone would lose you. Think about that. The strange effect at the center of tonight's whole journey, time running at different speeds at different depths in gravity, is not exotic. It is not theoretical. It is a line item in the maintenance of a system you use today to find a coffee shop. And if that small, gentle version is real enough to engineer around, real enough that ignoring it would strand you miles from where you think you are, then the violent version, the one near the black hole where the effect grows from millionths of a second into millions of years, is real too. It is the same effect, the same physics, just turned up by the heaviest object in the galaxy until it stops being a correction and becomes the entire experience. The blue dot on your phone and the frozen image of a falling body at the edge of a black hole are two readings of the same dial, one whispered, one screamed. As you fall toward the horizon, your time slows down relative to everyone you left behind. From your point of view, your clock ticks along normally, 1 second per second, the way it always has. You feel nothing strange, but the universe behind you begins to speed up. The stayed-behind clock runs faster and faster, and if you fell slowly enough, lingered near the horizon long enough, you might watch the entire future of the universe play out behind you, sped up. Like a film on fast-forward, stars flaring and dying, the galaxy turning, everything you ever knew aging and ending while you hang there, falling, in what feels to you like no time at all. That is not science fiction. That is the geometry of the thing. The closer you get to the horizon, the more extreme the gap between your clock and theirs becomes, until, right at the horizon itself, the gap becomes infinite. To the people watching from far away, you never quite cross. You slow and redden and dim and freeze, hovering forever at the edge, a fading photograph pinned to the door. But to you falling, there is no freezing at all. You cross right through, in real time, on your own ordinary clock, while behind you eternity quietly runs out. If you have ever seen the film Interstellar, you have already felt a version of tonight's strangeness, and it is worth pausing on, because that film got something profoundly right, and the rightness was not an accident. There is a scene where the crew lands on a planet orbiting close to a giant black hole. They are on the surface for what feels to them like a few hours, wading through shallow water, dealing with a problem. And when they return to their ship, the crewmate who stayed behind, who did not go down to the planet, has aged by 23 years. 23 years against their few hours. He has been up there, waiting, watching, growing old, while they barely lived an afternoon. That is not a screenwriter's fantasy. That is exactly the effect we have been living tonight. And the reason it is in the film at all is that the physicist Kip Thorne, one of the people who has thought hardest about black holes in the last half-century, worked directly on the movie and insisted the science be real. The planet sits so deep in the black hole's gravity that time there crawls relative to the ship far above. 1 hour on that surface really would equal years outside. Thorne worked out the numbers. He even required that the black hole be spinning at a tremendous rate to make the time dilation that extreme while still letting the planet survive, and the result is real physics dressed as a story. And here is the thing I find quietly devastating about that scene. The thing that goes beyond the spectacle. The horror of it is not a monster. The horror is the arithmetic. The crewmate did nothing wrong. He simply stayed in a place where time ran differently, and the cost was most of his life, and the people below missed it, lived right through it, never felt it pass. 2 people in the same star system, on the same day, and one of them spends an afternoon while the other spends a quarter of his life. Both clocks, honest. Both experiences real. Nobody to blame, just geometry. That is what you are doing tonight, but more so. The planet in the film only flirts with the edge. You're going all the way in. The crewmate aged 23 years against their afternoon. The people you left behind as you cross the true horizon will not age 23 years. They will age past every number we have, past the lifetime of the sun, past the lifetime of the galaxy, while you fall through your final calm minute. The film showed you a sip of it. We are drinking the whole glass, and the most haunting part for me is the same in both cases. No alarm sounds when this happens. No one feels the wrongness in their own body. Each person's own clock the whole time just ticks along, telling them the patient, local, ordinary truth. I want to pause here, because we just said something enormous and the channel runs on moments like this one. If you're lying there in the dark and that idea just landed, the idea that the same fall can take 2 hours for the one falling and forever for the one watching, that both of those are true at once, that the universe genuinely allows this, then take a second to like the video or subscribe. I am not going to make a big thing of it. It just helps these slow, strange ideas reach a few more people who would rather think about time bending around a black hole at 3 a.m. than be sold something. If you're listening on Spotify, the follow button does the same quiet work. That is all. Your fall continues either way, and it does continue. While we were talking, you fell further. The dark sphere is bigger now. It is no longer something you could cover with your thumb. It spreads across a good part of the sky ahead, rimmed with that gathered brightening light, and the stars behind you have thinned to a shrinking pool. You're not in danger yet. Your body is still whole, still weightless, still calm. But the clock behind you is racing now, and somewhere out there, while you fall through what feels like a few quiet minutes, years are going by. Let me tell you how we know any of this is true, because it would be fair right now to wonder whether this is all just math on a chalkboard, a story physicists tell. It is not. We have seen it. and the seeing of it is one of the great quiet achievements of the last few years. For most of human history, a black hole was an idea, a solution to some equations that Einstein himself was not sure described anything real. He wrote down the theory of gravity in 1915, and within months a physicist named Karl Schwarzschild, working out the math from a trench on the First World War's Eastern Front, found that the equations allowed for something bizarre, a region where gravity became so strong that not even light could leave. Schwarzschild died of illness a few months later, and the strange object that fell out of his calculation sat in the theory for decades like a splinter no one wanted to touch. Even Einstein wrote a paper arguing these things could not actually form in nature. He was wrong, but you can understand why he resisted. The object was too strange to believe. It took the rest of the century to come around. Through the 1960s and 70s, as the math got clearer and as astronomers started finding objects in the sky that nothing else could explain, the splinter became impossible to ignore. By the time I was learning any of this, black holes had gone from heresy to near certainty. But near certainty is not the same as seeing, and no one had ever seen one. By their nature, they give off no light. How do you photograph a thing whose entire definition is that nothing comes back from it? You photograph its shadow. That was the insight. You cannot see the black hole, but if it sits in front of something bright, that ring of glowing gas we talked about, then the black hole will carve a dark silhouette out of the glow, and the exact shape and size of that silhouette is something the theory predicts precisely. Find the shadow, measure it, and you are testing Einstein right at the edge of the abyss. The trouble is that these things, even the supermassive ones, are absurdly far away, and their shadows on our sky are absurdly small. Sagittarius A star, our own galaxy's giant, casts a shadow that, from Earth, is about the size of a donut sitting on the surface of the moon. To photograph a donut on the moon, you would need a telescope the size of the Earth. So they built one. Not literally a single dish the size of the planet, but something clever enough to act like one. The Event Horizon telescope linked together radio observatories scattered across the whole globe, from Hawaii to Chile to the South Pole to the mountains of Spain, all staring at the same point in the sky at the same instant, their data stitched together so precisely that the array behaved like one telescope as wide as the Earth itself. It took years. It took petabytes of data, so much that it was faster to fly hard drives across the world on airplanes than to send the data over the internet. And in April of 2019, they showed the world the result. A ring. A blurry, glowing orange ring of light, with a dark hole punched through its centre. The first photograph of a black hole's shadow. This one in a galaxy called M87, 55 million light-years away. A monster 6.5 billion times the mass of our sun. It looked, honestly, a little humble. A fuzzy orange smudge. But that smudge matched what the equations had predicted. Down to the size, down to the shape, and 100 years of theory suddenly had a face. Then, in 2022, they did it again, this time for Sagittarius A star, the giant at the centre of our own galaxy, the very kind of object we're falling into tonight. Another ring, another shadow, right there in our own cosmic backyard. Here is the thing I find quietly moving about those pictures, and it bears directly on our fall. That bright ring is not just gas. Part of the light in that ring is something more haunting. Some of those photons did not come straight from the gas to the camera. Some of them came off the gas, swung all the way around the back of the black hole, looped around it like a ball on a string, and only then flew toward us. You are, in part, looking at the back of the black hole wrapped around to the front, carried by light that orbited the abyss before escaping. There is a region just outside the horizon where gravity is strong enough to bend the path of light into a circle. It is called the photon sphere, and we are about to fall through it. There is a paradox about black holes that I love, and we have been circling it all night without naming it. The darkest objects in the universe are also responsible for the brightest. The very same thing that lets nothing escape is, in another mood, the engine behind the most luminous lighthouses in all of creation. Here is how that works, and it bears on the disk of light we have been falling toward. When gas falls toward a black hole, it almost never falls straight in. It has a little sideways motion, like water circling a drain, so it settles into a flat spinning disk and spirals inward gradually. And as it spirals, it crowds. The inner parts orbit faster than the outer parts, so the layers grind against each other, and the friction heats the gas, and the deeper in it goes, the hotter it gets, until the inner edge of the disk, just outside the horizon, can reach temperatures of millions of degrees. Gas that hot does not just glow, it blazes across the whole spectrum in visible light and ultraviolet and X-rays pouring out energy. And the efficiency of this is staggering. When you drop matter toward a black hole and let it heat up in that disk before it falls in, you can convert something like 10 to 30% of the matter's mass directly into light. Compare that to the nuclear fusion that powers the sun, which converts less than 1% of its fuel's mass into energy. Falling into a black hole is, pound for pound, one of the most efficient ways the universe has of turning matter into light. The trap is also a furnace, and that raises a strange possibility that the darkest things make the brightest light. When this happens around a supermassive black hole that has plenty to eat, the result is called a quasar, and quasars are the brightest sustained objects in the entire universe. A single one can outshine its entire host galaxy, all 100 billion stars of it, from a region not much bigger than our solar system. We see quasars from across almost the whole observable universe, their light having travelled for billions of years to reach us, beacons marking where giant black holes were feeding when the cosmos was young. The light you see from the most distant quasars left them before the Earth existed, and it is, at its heart, the glow of matter screaming as it fell toward exactly the kind of object you are falling into tonight. So as you drop through the brilliant ring around your black hole, understand what that light is. It is the last radiance of everything else that fell before you. Gas, dust, stars torn apart, all of it heating to a fury and shining one final time on its way across the horizon. The disk is a chorus of everything the black hole has ever eaten, singing as it goes down. And you are falling through the chorus toward the silence at the centre, where the singing finally stops because nothing past the horizon can send its light back out to join the song. You move from the brightest place in the universe to the darkest in a single quiet fall, and the boundary between them is the line you cannot feel. Think about what that means for what you will see. As you cross the photon sphere on your way down, you enter the region where light itself can orbit. Look to the side and you might see the back of your own head, light that left you, circle the black hole, and return to your eyes from the other direction. Look ahead, and the gathered, ringed, distorted light of the entire universe is now compressed into a brilliant band. The sky is no longer a sky. It is a lens, a funhouse mirror wrapping the whole cosmos into shapes that no eye evolved to read. And all of this, every bit of it, the shadow, the ring, the looping light, has now been photographed in the real sky, by real telescopes, exactly where the theory said it would be. We are not falling through a fantasy tonight. We are falling through a place that has had its picture taken. The donut on the moon turned out to be real, and you're dropping straight toward the hole in the middle of it. I mentioned in passing that we have heard black holes collide, and I do not want to let that go by as a throwaway, because it might be my favourite thing humans have ever done, and it makes everything tonight feel solid under your feet. For most of history, we studied the universe entirely with light. Telescopes catch light in all its forms, and from that light we reconstruct everything. But black holes give off no light, so for a long time, the most dramatic events involving them, two black holes spiralling into each other and merging, happened in complete silence and darkness, utterly invisible to us. We knew they must happen. We had no way to witness them. Then, in September of 2015, we did. Einstein's theory predicted that when massive objects accelerate violently, they should send out ripples in the fabric of space-time itself, waves that stretch and squeeze space as they pass, spreading outward at the speed of light. Gravitational waves. He predicted them in 1916 and assumed gloomily that they would always be far too faint to ever detect, because the stretching they cause is almost unimaginably tiny. To catch one, you would need to measure a change in length thousands of times smaller than the nucleus of an atom, across a distance of miles. So they built a machine that could do exactly that. 2 of them actually called LIGO, each one a pair of tunnels several miles long, arranged in an L, with laser light bouncing back and forth along them, watching for the moment when a passing ripple stretched one arm and squeezed the other by that absurdly tiny amount. It took decades, and it sounded to many like an impossible dream. And then one morning the machines twitched, both of them, in the same pattern, a few milliseconds apart. A gravitational wave had washed through the Earth. When they decoded its shape, the story it told was breathtaking. More than 1 billion years ago in a distant galaxy, 2 black holes, each about 30 times the mass of the Sun, had been locked in a death spiral, whirling around each other faster and faster until they slammed together and merged into one. In the final fraction of a second, they radiated more energy in the form of these space-time ripples than all the stars in the entire observable universe combined were giving off in light at that moment. The wave spread out, crossed 1 billion years of space, and arrived, faint as a whisper, to nudge a laser in a tunnel on a small wet planet where, in the meantime, someone had been clever enough to be listening. And here is the part that gives me chills. If you take that signal and play it as sound, because the frequencies happen to fall in the range of human hearing, you can listen to it. It is a rising tone, a swoop upward, ending in a little thump, and physicists call it the chirp. It lasts about 1/5 of a second. That chirp is the sound, if you want to call it that, of 2 black holes becoming one, recorded here on Earth 1 billion years after it happened. We have built ears for the universe, and the first thing they heard was the collision of the very kind of object you are falling into tonight. So when I tell you this fall is real, I am not pointing at a chalkboard. I am pointing at a sound we caught with our own instruments. The ringing of space-time itself, struck like a bell by the merging of 2 black holes, and still arriving. Let me ground all of this somewhere real, because we keep saying Sagittarius A star, the giant at the centre of our own galaxy, and I do not want it to stay an abstraction. We know an astonishing amount about that particular black hole, and the story of how we came to know it is one I find genuinely moving. For about 30 years, 2 teams of astronomers, one in Germany led by Reinhard Genzel, one in California led by Andrea Ghez, did something that sounds impossible. They watched individual stars orbit the centre of our galaxy, not the glow of the centre, not a blur, but specific, named stars, tracked one by one, night after night, year after year for decades. The centre of the Milky Way is about 26,000 light-years away, buried behind thick clouds of dust, and to see those stars at all, they had to invent new techniques to undo the blurring of Earth's atmosphere in real time. And slowly, over the years, the orbits emerged. What they saw was a cluster of stars whipping around something invisible. One star in particular, a blazing fast one called S2, makes a complete orbit every 16 years, and at its closest approach it is moving at nearly 3% of the speed of light, something like 16 million miles per hour. Stars do not move like that unless something enormous and unbelievably compact is pulling on them. By tracking the precise shape and speed of those orbits, the 2 teams could weigh the invisible thing at the focus. The answer came back the same from both. About 4 million times the mass of the Sun, packed into a region smaller than the orbit of Mercury. There is no known object that can be that heavy and that small except one. A black hole. Genzel and Ghez shared the Nobel Prize for it in 2020, and Andrea Ghez became only the fourth woman ever to win the physics prize. And it gets better, because S2's orbit did something Einstein predicted and Newton could not explain. As that star swung around the black hole at its blistering closest approach, the light it gave off was stretched, reddened, by climbing out of the black hole's gravity. The exact same effect we have been falling through tonight, measured in a real star around our real galactic center. And the orbit itself does not quite close into a clean repeating ellipse. It precesses, it rotates a little with each pass, exactly the amount general relativity says it should. We are not guessing about this black hole. We have watched stars dance around it for 30 years and clocked the dance against Einstein to the decimal place, and Einstein keeps winning. So when I ask you to fall into a supermassive black hole tonight, I am not asking you to imagine a fantasy. I am asking you to fall into that one, the real one, 26,000 light years straight down through the heart of the galaxy you live in, to a place we have weighed and photographed and watched bend the paths of stars and the colour of their light. It is there right now, as you lie in the dark. The centre of everything we belong to is a great silent mass that swallows time. And the same physics that keeps your phone honest about which street you're on is the physics that, turned all the way up, governs the thing at the middle of the Milky Way. The journey tonight is impossible only because of the distance. Everything else about it is as real as the floor under your house. So let us return to the fall, because while I was telling you how we learned to see these things, you got much, much closer. The ring is a s now. It fills your view, and your clock, your own faithful clock, is about to enter the strangest hour of its life. We are getting close now, close enough that I want to slow the fall down and walk you through the crossing itself, moment by moment, because this is the part everyone wants to know about and almost no one describes honestly. What does it actually feel like to cross the event horizon of a black hole? The answer, for our giant, is the most unsettling answer of all. It feels like nothing. There is no membrane, no barrier, no flash. The event horizon is not a place where space suddenly changes texture. It is not made of anything. It is a purely mathematical surface defined by a single property, that past this line, every possible path forward leads deeper in. You could cross it with your eyes closed and never know. There is no instant where you feel yourself pass. One moment you're outside the most absolute boundary in the universe, and the next you're inside it, and your body reports no difference at all. Your clock keeps ticking, your heart keeps beating, you are still you, still whole, still falling, still calm, and yet everything has changed. Because the universe has just quietly closed behind you. Let me be careful and exact about what that means, because it is the true horror of the thing, and it is a quiet horror, not a loud one. Crossing the horizon does not kill you. It does not hurt you. What it does is remove every future in which you leave. Before the crossing, you might, in principle, have fired a rocket, turned around, climbed back out, gone home. It would have been hard, but it was possible. After the crossing, it is not hard. It is impossible, in the deepest sense the word has. There is no direction labelled out anymore. The centre of the black hole is no longer a place in space you could choose to avoid. It has become a moment in your future, as unavoidable as next Tuesday. You cannot steer away from it any more than you can steer away from tomorrow. Down has stopped being a direction. Down has become a time. That is the sentence I most want you to carry out of tonight. Inside a black hole, the centre is not somewhere you are going. It is someone you are going. The singularity is not in front of you. It is ahead of you, in time, and every second brings it closer the way every second brings the future closer, and nothing you can do, no engine, no struggle, no genius, can buy you a single extra moment. The fall has become the same thing as the flow of time itself. We have been talking about you falling in, one person, intact, sailing calmly through the horizon of a giant. But the universe does this to whole stars, and we have watched it happen, and the watching is worth a few minutes because it shows you the violent version of the fall you're taking gently. When a star wanders too close to a supermassive black hole, it does not get to cross the horizon in one peaceful piece the way you are doing tonight. A star is enormous, far wider than your body, and so the tidal force, that difference in gravity from the near side to the far side that we have talked about, acts across the whole width of the star. The near side gets pulled vastly harder than the far side, and if the star crosses a certain distance, the difference becomes greater than the star's own gravity holding it together, and the star comes apart. It is torn, stretched into a long stream of glowing gas, half of it flung outward, half of it whipping around the black hole and falling inward. Astronomers call this a tidal disruption event, and the phrase is clinical for something genuinely violent. A sun unmade in a matter of hours. And here is the thing, we see them. Every so often, a telescope catches a galaxy's centre suddenly brightening, flaring up over weeks, blazing for months, then slowly fading over years. When astronomers study the flare, the story it tells is always the same. A star, often something like our own sun, drifted too close to the central black hole, was torn apart, and the shredded stream of its gas spiraled in, heating up as it crowded toward the horizon, blazing out across space as it went. We are, in those moments, watching a star die not by exploding, not by burning out, but by being eaten. The flare is the star's last light as it falls. There was one in 2019 catalogued with a string of letters and numbers the way these things are, that astronomers watched in exquisite detail, tracking the brightening and the fade, reading in the light the temperature and the speed and the chemistry of a sun being pulled into ribbons. There have been others since, dozens now, a whole growing catalogue of stars caught in the act of falling. Each one is a giant black hole, often quiet for centuries, suddenly betraying its presence by the light of something it just destroyed. The black holes are dark and silent until they eat, and then briefly, they shine with the death of whatever they swallowed. I tell you this so the gentleness of your own fall lands properly. You're crossing the horizon of a giant intact, calm, whole, because you are small, far smaller than a star, and the tidal force across your body at the giant's horizon is mild. A whole star, spread across more than 1,000,000 miles, cannot say the same. It feels the difference in gravity across its vast width and it tears. So in a strange way, your smallness is a mercy. The same black hole that rips a sun into a glowing stream lets a single human body drift across its edge without a sound. You will be unmade too, eventually, in the final fraction of a second near the centre. But you get the quiet version, the long, calm fall first, precisely because there is so little of you. The stars get the violence. You get the descent. There is one more property of our black hole I've been quietly leaning on without explaining, and it changes the character of the place in a way worth a few minutes. Our black hole spins, and a spinning black hole is a far stranger thing than a still one. Everything in the universe rotates. The Earth spins, the Sun spins, the galaxy turns. When a giant star collapses, or when a black hole feeds on a swirling disk of gas, all of that rotation has to go somewhere, and it gets concentrated, so real black holes spin, often ferociously, some of them whirling around close to the ultimate speed limit that the physics allows. And when a black hole spins, it does something that sounds like mysticism but is solid, tested relativity. It drags space itself around with it. Picture the black hole sitting in space like a spoon in honey. As the spoon turns, it pulls the honey around with it in a slow swirl. A spinning black hole does this to space-time. The very fabric of space near it is caught and dragged into rotation, whirled around the black hole whether anything wants to go that way or not. This is called frame dragging, and it is not a metaphor. We have measured a whisper of it around the Earth itself, with satellites delicate enough to feel our own planet's tiny twisting of space as it spins. Around a fast black hole it is no whisper, it is overwhelming, there is a region around a spinning black hole just outside the horizon, called the ergosphere, where this dragging becomes so total that nothing can stand still. Not you, not light, not anything. Inside the ergosphere, space is being swept around so forcefully that to remain motionless you would have to travel faster than light in the opposite direction, which nothing can do, so you simply cannot stay put. You are forced to rotate with the black hole, carried along on the current of space itself, even if you are still, in principle, able to escape outward. It is a place where staying still is not forbidden by a rule, but by the shape of reality. There is no such thing as standing your ground inside the ergosphere. The ground itself is moving. The spin changes the inside too, and this connects back to the third door I mentioned near the centre. A still black hole, in the simplest math, ends in a point, but a spinning one, because of all that whirling, ends not in a point but in a ring, and it is the geometry of that spinning ring that opens up those strange theoretical passages, the maybe tunnels we talked about, the ones almost certainly sealed by reality but tantalizing on paper. The spin is what cracks the door open, even a sliver. A motionless black hole is a dead end. A spinning one, at least in the pure equations, has a stranger structure at its heart, a ring instead of a point, and a question instead of a wall. So the black hole you're falling into tonight is not a calm, dark sphere after all. It is a whirlpool, dragging the fabric of space into a vortex around itself, and somewhere as you fell you crossed into the region where you could no longer have stood still even if you tried, where space took you by the hand whether you reached out or not and turned you with it. You have been swept, this whole last while, in the slow spin of the thing, carried around as you fell inward, riding a current that is not in the space but is the space. And you never felt that either. Your own small clock, your own calm body, sensed nothing but the quiet of the fall. Now here is the question that follows naturally, the one you are probably already asking. If I have crossed, and I cannot get out, and the centre is coming, how long do I have? For our supermassive black hole, the answer is gentle by the standards of these things. From the moment you cross the horizon of a giant like Sagittarius A star to the moment you reach the centre, you have something on the order of a minute, maybe a little less. For a black hole of a few million solar masses, the time from the horizon to the heart is roughly that. A minute of falling inside. For the bigger giants, the billion solar mass monsters, it could be longer, many minutes, even hours for the truly colossal ones. The bigger the black hole, the longer the grace period inside. I keep calling our black hole a giant, 4 million times the mass of the Sun, and that is true. But I want to give you a sense of where it sits in the family, because 4 million suns, as enormous as that is, turns out to be on the smaller end of the supermassive class, and the largest ones are almost difficult to talk about honestly. Our Sagittarius A star is, by the standards of these objects, modest. A tidy 4 million solar masses. The one at the centre of the galaxy M87, the one we photographed first, is far larger, around 6.5 billion solar masses, more than 1,000 times heavier than ours. Its horizon is so wide that our entire solar system, Sun and all the planets and most of the comet clouds beyond, would fit inside it with room to spare. You could drop the orbit of Pluto into that black hole and lose it completely. And M87's giant is not the largest. The biggest black holes we have found are called ultramassive, and they reach tens of billions of solar masses. One of them, a distant quasar with the unromantic name TON 618, is estimated at something like 66 billion times the mass of the Sun. 66 billion suns in a single object. Its horizon would be so large that light, the fastest thing there is, would take days just to cross it. Days. A beam of light which crosses from the Sun to the Earth in 8 minutes and crosses our entire solar system in less than a day would need the better part of a week simply to traverse the width of that one black hole's point of no return. Here is what that does to our fall, and it is worth sitting with. The bigger the black hole, the gentler the crossing and the longer the calm fall inside. because everything is stretched out, the horizon vast, the gravity changing slowly across the span of your body. Into our 4 million solar mass giant, you have about a minute between crossing the horizon and reaching the centre. Into one of the ultramassive monsters, you might have hours of calm falling inside the horizon before the end. Hours in the unknowable interior, conscious and whole, with the universe's whole future blazing in the window above you before the tidal force finally finds you near the centre. The largest black holes offer the longest, strangest, most patient deaths in the universe. If you wanted the most time to think on the way down, you would choose the biggest one you could find. And these things are real and catalogued and scattered through the cosmos by the millions. Almost every large galaxy has one at its heart. They are not rare monsters lurking at the edge of possibility. They are a standard feature of the universe, one to a galaxy, holding the centre, bending the time around them, occasionally flaring as they feed. The night sky, if you could see these objects directly, would be salted with them, a giant at the core of nearly every smudge of light you can name. We live in a universe built around them, and the one at the centre of our own galaxy, our modest 4 million suns, is, on this scale, the gentle neighbour. Tonight you fell into the small one. Somewhere out there are doors 1,000, 10,000 times wider, each one holding its own minute or hour of quiet falling, each one keeping its own secret at the centre. I called our black hole a giant and left it at that, but the family of these objects is worth knowing, because where ours came from is its own quiet mystery, and the mystery is unsolved in a way that I find more interesting than any tidy answer. There are, roughly, 3 sizes of black hole in the universe, and the gap between them is part of the puzzle. The first kind, the small ones, we have met already. They form when a massive star, far bigger than our sun, runs out of fuel and collapses under its own weight. The core falls inward, and if the star was heavy enough, nothing can stop the collapse, and a black hole a few to a few dozen times the mass of the sun is born in the heart of a dying star. These we understand well. We have watched them form. We have heard them collide, which is its own astonishing story. 2 of them spiralling together and ringing space-time like a bell, a ripple we caught here on Earth in 2015 with instruments that can sense a wobble smaller than the width of a proton. The third kind are the giants, the supermassive ones, millions to billions of times the sun, sitting at the centres of galaxies, ours, and here is the puzzle. We are fairly sure the small ones form from dying stars, but you cannot make a 4 million solar mass black hole by collapsing a single star. There is no star that big. So how did the giants get so giant? They must have grown, swallowing gas and stars and smaller black holes over billions of years. But when we point our best telescopes at the very early universe, we find supermassive black holes that are already enormous when the cosmos was only a few 100 million years old. Far too young, it seems, for them to have grown that big by ordinary feeding. They are too big, too soon. It is one of the genuine open problems in astrophysics right now, sharpened in just the last couple of years by the James Webb Telescope, finding these early giants in even greater numbers than expected. Nobody is fully sure how the monsters got made. And then there is the missing middle. The medium-sized black holes, hundreds to thousands of times the sun, the ones that should bridge the gap between the small and the giant, are oddly hard to find. For a long time we had almost none. We are only now in recent years starting to find convincing examples of these intermediate black holes, and each one is a small triumph, a missing puzzle piece slotting into place. The fact that they are so rare or so well hidden is itself a clue about how the giants assembled, though a clue we are still learning to read. I tell you all this so that when you fall with a sense of the thing's history. The giant you're dropping into was not always a giant. It began most likely smaller and grew over more than 10 billion years, feeding on everything that wandered too close, merging with other black holes when galaxies collided, swelling slowly across an expanse of time so large that the entire history of life on Earth is a recent chapter within it. You're not falling into an object, you're falling into an outcome, the end product of billions of years of patient accumulation, a thing that ate its way to the center of a galaxy and has been sitting there quietly bending time since long before there was anyone to fall into it. And tonight, in real time, on your own small clock, you finally do. And in that time, you are not yet being harmed. This is the part that surprises people most. For most of your fall inside the horizon, you remain whole and comfortable. The stretching, the spaghettification, does not happen at the horizon of a giant. It happens much later, much deeper, very close to the center, in the final fraction of your remaining time. So for most of your minute inside, you simply fall, intact, conscious, looking around at a place that no information has ever escaped to tell us about. You are in those moments somewhere genuinely unknown. Every word anyone has ever spoken about the inside of a black hole is theory. No signal comes back. You might be the only human being who ever knew, and you would have no way, ever, to tell anyone. Let me explain spaghettification properly, because I have used the silly word twice now, and waved at it, and the real mechanism is something you can actually feel the logic of sitting where you are, and it connects, of all things, to the ocean. The force that would stretch you near a black hole is not some exotic new thing. It is a tidal force, and it is the very same force that makes the tides rise and fall on Earth every day. Here is the idea. Gravity gets weaker with distance. The closer you are to a massive object, the stronger its pull. That sounds simple, but it has a consequence that hides in plain sight. If you're falling towards something, the parts of you that are closer to it feel a slightly stronger pull than the parts of you that are farther away. Your feet, if they are leading, get pulled a little harder than your head. The difference tries to stretch you. On Earth, you feel a version of this constantly and never notice. The moon pulls on the side of the Earth facing it slightly harder than it pulls on the far side. That small difference in pull, across the whole width of the planet, is enough to raise the oceans into bulges on both sides, and as the Earth turns beneath those bulges, we get 2 high tides and 2 low tides a day. The tides are gravity's difference, made visible in water. Every time you have stood on a beach and watched the sea climb the sand, you are watching a gentle, ocean-sized version of the exact force that would one day pull a person into a thread near a black hole. Now turn that force up. Near a small black hole, the gravity changes so steeply over the few feet of a human body that the difference in pull between your head and your feet becomes enormous. Hundreds, then thousands, then millions of times your own weight, pulling you apart lengthwise while squeezing you in from the sides, because the lines of gravity funnel inward toward a single point. You would be stretched and narrowed at once, drawn out into a long thin filament, exactly like a strand of pasta. Hence the word. It is a ridiculous word for a genuinely grim process, and physicists use it precisely because the image is so accurate. The reason we chose a giant tonight, the reason your fall has been so calm, is that this tidal difference depends on how sharply gravity changes, not just on how strong it is. Around a supermassive black hole, the horizon is so vast and so far from the center that gravity changes very gradually across the span of your body as you cross. The difference between your head and your feet, right at the horizon of a 4 million solar mass giant, is mild, survivable, barely noticeable. That is why you sailed through intact. The stretching only becomes lethal much later, very close to the center, in the final fraction of a second, when even the giant's gravity finally starts changing steeply enough to matter. The tide that drowns you was always coming. We just chose the black hole big enough that it held off until the very end and gave you the whole long fall in peace first. But let us talk about what you see, because even here, the theory has things to say, and they are strange and beautiful. Turn and look back the way you came, back toward the horizon you crossed. You might expect darkness behind you, the closing door, but it is not dark. The horizon, from the inside, is not a wall. The light of the outside universe is still falling in along with you, still reaching your eyes, and it is gathered now into a shrinking, brilliant window above you, the entire external cosmos compressed into a bright shape overhead, growing smaller and more concentrated as you fall. Everything outside, every star, every galaxy, all of it, funneled into that one closing aperture of light. And because time outside is now running so extraordinarily fast compared to yours, that window is showing you the future. In your final falling minute, the universe above you may age by an unimaginable span. You might, in principle, watch the cosmos grow old in the skylight above your head, while you drop in real time on your own slow clock toward the center. Expectation. Falling into a black hole means sinking into darkness. Reality. It may mean falling away from a single shrinking window of blinding accelerated light, the last and brightest thing you ever see, holding the whole sped-up history of everything you ever loved. We have only a little of the fall left now. The window above is small and fierce. The center is close, not in space, but in time, the way a held breath is close to its end. Let us spend our last minutes well and talk about what waits at the bottom and what it would actually do to you, and whether, just maybe, the bottom is not the end of the story after all. So what is down there? What is the center of a black hole actually made of? The honest answer, the one a physicist will give you if they are being truthful, is that we do not know. And I want to be careful here, because this is the place where it would be easy to make something up, and the real situation is more interesting than anything I could invent. When you take Einstein's equations, the ones that have passed every test we have ever thrown at them, including those photographs of the shadow, and you follow them all the way down to the center of a black hole, they give you an answer that physicists do not actually believe. They tell you that all the mass collapses to a single point of zero size and infinite density, a place where space curves infinitely sharply, where the equations stop producing numbers and start producing infinities. That point is called the singularity, and when a theory hands you an infinity, it is almost never telling you that the universe really becomes infinite there. It is telling you that your theory has reached the edge of what it understands. The infinity is not a description, it is a confession. So the singularity is best understood not as a thing we know about, but as a question mark the size of a universe. It is the place where general relativity, our magnificent, perfect so far theory of gravity, breaks down and admits it needs help. The help it needs is a theory that combines gravity with quantum mechanics, the physics of the very small, and we do not have that theory yet. People have spent their entire careers reaching for it. String theory, loop quantum gravity, others. Tonight, as you fall toward the center, you are falling toward the exact spot where the deepest unsolved problem in physics lives. The bottom of a black hole is where human knowledge currently ends. There is a thread I left hanging, and it is too good to leave, because it touches the one way a black hole is not quite the perfect prison it appears to be. I told you that nothing escapes a black hole. That is what the horizon means. But in the 1970s, a young physicist named Stephen Hawking found a loophole, and it is one of the strangest and most consequential ideas in modern physics. Hawking was thinking about what happens at the horizon when you take quantum mechanics seriously. And quantum mechanics says that empty space is not really empty. Down at the smallest scales, it churns. Pairs of particles are constantly flickering into existence, and then annihilating each other almost instantly, borrowing a little energy from the vacuum and paying it back before anyone notices. This happens everywhere, all the time, even in the room you're lying in. It is a well-tested feature of reality, not a guess. Now picture one of those flickering pairs appearing right at the edge of the horizon. Ordinarily, the two would meet again and vanish, but at the horizon, something can go wrong. Beautifully wrong. One of the pair can fall in, across the point of no return, while the other escapes outward, away from the black hole before they can reunite. The one that escaped is now a real particle, carrying real energy, flying off into space. And to balance the books, the black hole has to pay. It loses a tiny bit of mass. The black hole ever so slightly shrinks. This is Hawking radiation. It means black holes are not perfectly black. They glow incredibly faintly, leaking energy one stray particle at a time, and over unimaginable spans of time they evaporate. They shrink, and as they shrink they glow a little brighter and leak a little faster, until at the very end, after a stretch of time that makes the current age of the universe look like an eye blink, they vanish in a final flicker. Here is the scale of it, and it is almost comical. For a supermassive black hole like the one we fell into tonight, the evaporation is so slow as to be almost meaningless on any human or even cosmic timescale. We're talking about something like 10 to the 100th power years. That is a 1 followed by 100 zeros. The universe is currently about 10 to the 10th power years old. So the black hole will outlast the present universe by a margin so vast that the words long after lose all meaning. The stars will burn out, the galaxies will scatter and go dark, the very last light in the cosmos will fade, and these black holes will still be there, glowing their imperceptible glow, slowly, slowly paying themselves out into the dark, the final structures in a universe that has otherwise ended. I bring this up not to frighten you, but for the opposite reason. The black hole you fell into tonight is, in the deepest possible sense, temporary, the most permanent seeming object in existence, the perfect trap, the place from which nothing returns, is itself slowly returning to nothing. Even it does not last. Even it's falling in its own way down a long, slow slope toward an ending. Everything in this universe is on its way somewhere, including the things that swallow everything else. There is a strange companionship in that, if you let yourself feel it. You and the black hole are not so different. Both of you are passing through. It is only the clocks that disagree on how long it takes. But let me tell you what the falling itself would be like in these final moments, because that part, the part before the mystery, the theory can describe. Remember spaghettification, the stretching we dodged at the horizon by choosing a giant. It was not cancelled. It was only postponed. It waited for us down here. As you approach the centre, the difference in gravity between your head and your feet, whichever is leading, grows and grows. At first it is a faint tugging, a sense of being gently pulled long. Then it is a stretch. Then, in the last instant, it becomes overwhelming, and you're drawn out into a thin stream, and the atoms of you follow, and whatever you were might stop being a body, and becomes a line of matter falling toward the point that the equations cannot describe. For a person falling into a supermassive black hole, this whole final act, from the first real tug to the end, takes a tiny fraction of a second. After a minute of calm falling, the end, when it comes fast. And then, by the only physics we have, you reach the singularity, and the story stops, because the theory stops, and no one can honestly tell you what happens next. Except, maybe, that is not quite the end. And I promised you a third door, so let me tell you about the one genuinely open possibility. The one that is speculation but is not nonsense. The simplest black holes, the ones in the simplest version of the math, end in that point. But real black holes spin. Everything in the universe spins, and the giants spin too, and when you solve the equations for a spinning black hole, something changes at the centre. The point becomes a ring. And in the pure mathematics of that spinning solution, the ring does not have to be a dead end. The equations, taken at face value, allow for paths that thread through the ring and come out, not back into our universe, but somewhere else. Another region of space-time entirely. This is where the idea of black holes as doorways comes from, and I told you at the start we were setting that idea aside. And we were, because here is the honest caveat. Almost no physicist believes you could actually survive such a passage, or that those tunnels are stable, or that they are anything more than a quirk of an idealized equation that the messy real universe might slam shut. The radiation falling in with you alone would likely seal the path. The portal is most likely not real, though the possibility lingers in the mathematics, but probably is not certainly. And there is something fitting on a night like this about falling toward a place where even the experts have to end their sentences with maybe. You're dropping into the one location in all of existence where our knowledge genuinely runs out, where the smartest people who ever lived can only shrug and point at the math and say, beyond here, we truly do not know. Most of the universe we have figured out, or are figuring out. This one spot keeps its secret, and you, in your last falling second, would be the only being who ever learned it, and the universe has arranged things so that you can never ever pass it on. I want to come back to that frozen image of you at the edge, the one the outside universe keeps forever, because it connects to the single deepest argument in modern physics, and it might just be the strangest idea I will share with you tonight. The question is simple to ask and brutally hard to answer. When something falls into a black hole, where does its information go? By information, physicists mean something specific. Every object carries a kind of detailed description of itself, the exact arrangement of its particles, the precise story of what it is and how it got that way. And one of the most cherished rules in all of physics is that this information can never be truly destroyed. Scrambled, yes. Burned, smeared, lost to any practical hope of reading it, yes. But in principle, the universe never forgets. If you burn a book, the information is still there in theory, in the smoke and ash and light, recoverable by some godlike accounting. Physics had always insisted on this. The past leaves a complete trace, always. But a black hole seemed to break the rule. Throw the book past the horizon, and it is gone, sealed away where nothing returns. And then, when Hawking showed that black holes slowly evaporate, leaking away as that faint radiation until they vanish entirely, the problem became a crisis. Because Hawking's radiation, in his original calculation, was featureless. It carried no detail about what had fallen in. So if the black hole evaporates completely, and all that comes out is blank radiation, then the information in the book is not scrambled. It is annihilated, gone from the universe entirely, and that is supposed to be impossible. This is the black hole information paradox, and physicists have been arguing about it, seriously, brilliantly, sometimes bitterly, for almost 50 years. Stephen Hawking himself bet that information was lost and then decades later conceded he was probably wrong. The current best guess, and I want to be honest that it is still partly a guess, is one of the most beautiful ideas I know. The information is not destroyed, and it is not quite inside the black hole either. It may be smeared across the horizon itself, stored on that two-dimensional surface like writing on a soap bubble, and slowly, subtly leaked back out, encoded in the faint radiation, over the eons of evaporation. The book is not lost. The book is rewritten onto the surface of the door. This leads to an idea called the holographic principle, and it is genuinely dizzying. It suggests that everything that falls into a black hole, all of its three-dimensional fullness, can be completely described by information painted on its two-dimensional surface. The inside is, in some deep sense, a projection of the boundary. And some physicists suspect this is not special to black holes. They suspect the whole universe might work this way, that the three-dimensional world you're resting in tonight might be, at the most fundamental level, encoded on a distant two-dimensional surface, the way a hologram stores a 3D image on a flat film. We do not know if that is true, but it came out of thinking hard about exactly the fall you are taking. So here is the strange comfort, and I will set it gently beside the frozen image from before. When you fall in tonight, you may not simply vanish. The deepest reading of the physics suggests that the complete information of you, every detail, the whole pattern that made you who you were, does not get destroyed at the center. It gets preserved somehow on the horizon, and over an unimaginable span of time, trickled back out into the universe in a scrambled form that in principle still remembers you existed. The universe, even here, even at the edge of its most total trap, may keep the receipt. We do not fully understand how, but the leading guess is that nothing, not even the you that fell into a black hole, is ever truly completely erased. That is the center, a question mark, a confession written in infinities, a ring that might against all odds be a door and almost certainly is not, though no one can rule the possibility out entirely. We have reached the bottom of the fall, and the bottom of what anyone knows. There is a mirror image to everything we have discussed tonight, a kind of photographic negative of the black hole, and almost no one outside physics has heard of it. It is called a white hole, and thinking about it tells you something deep about why the universe runs the way it does. Here is where it comes from. The equations that describe a black hole, Einstein's equations, do not actually know which way time runs. The math is symmetric. You can run it forward or backward and it still works. And when you run the black hole solution backward in time, you get something that is its perfect opposite. A black hole is a region nothing can ever leave. Run it backward and you get a region nothing can ever enter. A place that only spits things out. Matter and light come pouring out of it, and nothing from outside can ever fall in. That is a white hole. Where a black hole is a perfect trap, a white hole is a perfect fountain. Where a black hole's horizon is a door you can only go in, a white hole's horizon is a door you can only come out of. The strange thing is that the mathematics permits white holes just as readily as black holes. They fall right out of the same equations, so the natural question is, where are they? If the math allows them, why does the universe seem to be full of black holes and utterly empty of their opposites? And the answer is one of the most quietly profound facts in physics. It comes down to time and to the difference between the past and the future. We live in a universe where time has a direction, where eggs break but do not unbreak, where smoke spreads out but never gathers itself back into the fire, where things fall together and settle, but do not spontaneously fly apart into order. This direction, this arrow of time, is tied to a quantity called entropy, the tendency of things to move from order toward disorder, and it only ever runs one way. A black hole is the ultimate expression of that arrow. It is matter falling together, settling, hiding, increasing the disorder of the universe in the most extreme way possible. It fits the direction time actually runs. A white hole runs against the arrow. It might be like watching the broken egg leap back together, the smoke gather back into the flame, but on a cosmic scale. The equations allow it, the way they allow a movie to be played backward, but the universe does not seem to do it, because it would require an almost impossibly special starting arrangement, the cosmic equivalent of every shattered piece spontaneously deciding to reassemble. So black holes form readily all over the universe, and white holes, as far as we can tell, do not form at all. Not because they are forbidden, but because they point the wrong way down the river of time. Some physicists have wondered whether the Big Bang itself, that moment everything poured out of, might be understood as a kind of white hole-like event, the one great fountain that the whole universe came out of. Others have wondered whether black holes that finish evaporating might just end in a brief white hole-like flicker. These are speculations, honest ones, edges of what we know. But the plain lesson of the white hole is the one I want to leave with you, because it reframes the whole fall. You can only ever fall in. You can never in this universe fall out. And that is not really a fact about black holes. It is a fact about time. The reason the black hole is a one-way door is the same reason the past is gone and the future is coming, the same reason this night moves forward and not back. The black hole is just the universe's arrow of time, drawn as sharply and absolutely as it can ever be drawn in a single dark circle against the stars. Let us turn around now, one last time, and look back up at that shrinking window of light, because there is a final thing to understand about this whole journey, and it is not about the center at all. It is about the part of you and the part of everyone that the black hole cannot quite swallow. Here is the last strange gift of the black hole, and it is the one I wanted to leave you with, because it is the gentlest thing in this whole hard story. You never really hit the bottom, not from the outside. Remember what we saw on the way down, the way your falling clock and the watching clock pulled apart, the way that to anyone left behind you slowed and reddened and dimmed and never quite crossed the horizon at all. That does not stop being true just because you, on the inside, fell all the way through. Both stories are real at the same time. You reach the center in about a minute, and the universe outside, the one that stayed behind, will never see it happen. To them, you're still there, frozen at the edge, a faint fading smear of light pinned to the door, growing dimmer over billions of years but never quite gone. There is a version of you, in a sense, that the black hole could not finish swallowing. A last image, held at the threshold, red shifting toward black so slowly that the universe will grow old before it fully fades. You fell, and you also, from the only vantage anyone outside will ever have, are still falling, will always be falling, caught in a single endless moment at the edge of the dark. I do not know what to do with that exactly, except to find it a little beautiful. The most total erasure the universe offers, the one place nothing escapes, and even it cannot quite agree with itself about when you are gone. Time bends so far that your ending has no single answer. A minute, and forever, both true, depending only on where you stand. There is a deeper lesson hiding inside the two clocks, yours and the watcher's, and I want to reach for it gently, because it is the kind of idea that is better felt than argued, and the dark and the late hour are the right conditions for feeling it. We have talked all night as though there were your time and their time, two clocks that disagree near the black hole. But here is the thing that took physicists a long while to accept, and that most people never quite do. There is no master clock. There is no true time that the universe keeps, against which yours and theirs are merely local errors. Both clocks are equally real, equally correct, and there is simply no fact of the matter about which one is the right one. The universe does not have a single, shared now. Think about what that means, slowly. We tend to assume that everything happening in the universe is happening at this moment, all together, a single great presence sliding forward everywhere at once. We say things like, I wonder what is happening right now on a planet across the galaxy. It feels like a perfectly sensible question. But relativity says it is not. There is no universal right now that stretches across space. What counts as the same moment depends on where you are and how you are moving, and for things far enough apart, the question of what is happening there now simply has no single answer. Two observers can genuinely disagree about which of two distant events came first, and neither of them is wrong. Simultaneity, the idea of two things happening at the same time, falls apart once you stretch it across the cosmos. The black hole takes this subtle, easily ignored truth and makes it impossible to ignore. Near the horizon, the disagreement between clocks does not stay polite and small. It grows without limit. Your minute and their eternity are not an illusion to be corrected. They are both simply true, two honest readings with no referee, the relativity of time stretched until you cannot look away from it. The black hole does not break the rule that time is local and personal. It just writes that rule across the sky in letters too large to miss. And there is, I think, a strange comfort buried in this, one I want to leave you with as the fall ends. If there is no universal now, then the moment you're in, right now, lying in the dark, your own quiet clock ticking, is not a small slice of some great cosmic present rushing past you. It is its own complete and valid reckoning of time, as real as any other in the universe, owned entirely by you. No black hole, no distant galaxy, no racing far-off clock has a more authentic now than the one you're holding right now in this room. Your time is not a copy of some truer time elsewhere. It is the genuine article. The universe hands each of us our own clock and tells each of us truthfully that ours keeps perfect time. Yours is keeping perfect time right now, slow and steady and real, carrying you gently through this night that belongs completely to you. let us go back for a while to that shrinking window of light above you, the one holding the sped-up future of the universe, because I rushed past it and it deserves a slow, patient look. It may be the most extraordinary view any conscious thing could ever have, and you, falling, are the only one positioned to take it in. Here is the setup again, gently. As you fall toward and through the horizon, your time runs slower and slower compared to the universe you left. From your point of view, your own clock is fine, 1 second per second. But the outside cosmos, glimpsed in that gathering window of light above you, is speeding up, faster and faster the deeper you go. So in the short span of your own fall, you might in principle watch an enormous stretch of cosmic history play out overhead, compressed, accelerated, like a film of the future on fast forward. So let us watch it together. In the first part of the fall, the window above shows you the ordinary sky, stars, the glow of your galaxy. But as your time slows, the film speeds up. Stars begin to flicker through their lives faster than seems possible, brightening and guttering out. The slow turning of the galaxy becomes visible, a vast pinwheel rotating where before it seemed frozen. Maybe you watch your galaxy and its neighbour drift together and merge, two great spirals folding into one over what feels to you like minutes but is, out there, billions of years. The window keeps shrinking and brightening, and the film keeps accelerating. And if you could fall slowly enough, lingering, the film would run all the way to the end. You would see star formation slow and then stop as the gas runs out, the galaxies dimming as their last bright stars die, and no new ones are born. You would see the universe redden and fade, the lights going out one by one, the long cooling, the slow drift toward darkness that the cosmos is genuinely, slowly headed for. The whole future, the actual far future of everything, compressed into the last moments of your fall and presented in a shrinking bright aperture above your head, like watching the end of the world through a closing skylight. There is something almost unbearably lonely and almost unbearably privileged about that view, and I do not want to pretend it is only one or the other. Lonely because you are watching everything you ever belonged to grow old and end, and there is no one beside you, and you cannot tell them, and you cannot go back. Privileged because no one else will ever see it. The whole history of the universe, its entire future, witnessed in a single falling minute by the one being positioned at the one vantage point that allows it. You become, for that minute, the only audience the end of the cosmos will ever have. I find I cannot decide whether that is the saddest thing I know or the most beautiful, and maybe it does not have to be decided. Maybe both are simply true, the way the minute and the eternity are both true, the way your slowing clock and their racing clock are both honest. You fall, and above you the universe lives out its entire life in fast forward, and you watch it go, calm and weightless and alone, holding in a single human gaze a span of time that no telescope, no civilization, no patient watcher on any world could ever hope to hold. Then the window closes and the film ends, and you turn back toward the dark below, carrying the whole future you just witnessed down with you into the one place it can never be told. And you, tonight, got to stand in both places. You fell all the way through, in real time, on your own clock these last 2 hours, from the first far-off glimpse of the dark sphere to the ring at the centre where knowledge ends. And you also stayed behind, here, in this room, in your bed, never moving, never in any danger at all, your own clock ticking softly and honestly the whole time, telling the truth it has always told you. That clock is still going now, 1 second, then the next, all the same size, all in a row. It never lied to you. It only ever measured your own small distance from the things that bend it. And here, far from any black hole, far from any horizon, it runs clean and slow and steady, the way it will run all through the night while you rest. The fall is over. You can let it go now. There is nothing to hold on to, and there never was, and that turned out to be the most restful part. You drifted down through the strangest place in the universe, and it asked nothing of you but to fall, and you did, and now you are here, whole, and the window of light above is just the ceiling, and the racing clocks were only ever a story about how far apart two things can drift, and both still be true. Breathe out. The dark around you is not the dark of the abyss. It is just the dark of a quiet room at the end of a long fall. Let your own clock carry you the rest of the way down, one honest second after another, into sleep. Sleep well.